fortunate today to have Geoff Vallis talk to us. Geoff's from Exeter. He's come here the long way via Santa Cruz, where he's on sabbaticals. We're very glad he's made the effort to come. Geoff's well known for his work on GFD, rotating fluids. Many of you probably have used his book. And today he's going to tell us about superrotation. Geoff.
Thank you, David, and thank you to the organisers for coming. I know you're only here for the wine reception afterwards, and guilt won't allow you to go to that without coming to the seminar. But anyway, thank you for coming. This is work. I was originally only going to talk about shallow atmospheres, but then Chris talked about Jupiter for a bit, and I thought I'd try and make a little bit of a connection with that. So the first part of my talk is going to be about deep atmospheres. And that's recent work with Lauren Matilsky and Nick Brummel, who are both at UCSC, Santa Cruz, and Matt Browning, who's at Exeter. The work on shallow atmospheres began over a decade ago with Jonathan Mitchell, who was then a postdoc, now is a professor, and it's potted on through the years with various collaborators. And much of the recent work has been done with Quentin Nicolas, who is a student actually at UC Berkeley. And Rayleigh, by the way, well, Daedalus and Isca and Rayleigh are all codes that we've used along the way. What is superrotation? It is when the atmosphere rotates faster than the planet beneath it, roughly speaking, and Jupiter superrotates at the equator. It's got prograde motion at the equator. We know pretty well the rotation rate of Jupiter from its magnetic field, and even if that was somewhat inaccurate, Jupiter would still be superrotating quite rapidly. Velocities of about 100–150 meters per second at the equator. More specifically, superrotation is when the average angular momentum of a ring of air exceeds that of the planet's surface at the equator. So it has more angular momentum than the planet does anywhere. And that's manifested in nearly all circumstances by prograde or eastward, defining eastward to be prograde, zonal atmospheric flow at the equator. So Earth does not superrotate. Occasionally it does under certain weather conditions to do with the quasi-biennial oscillation, but normally not. A number of planets do superrotate. In our solar system, Venus superrotates, Titan superrotates, Jupiter does, Saturn does, and some exoplanets do. The oceans on some of the icy moons also most likely do. Uranus and Neptune do not. Question we want to answer is why? What's the mechanism? Do all exoplanets superrotate, etc.? A few observations. On the right, we can see Jupiter and Saturn, the zonal wind on the bottom, latitude on the y-axis, and you can see Jupiter again superrotating, speeds of about 150, up to 150 meters per second. Saturn even more so, up to about 400 meters per second. And it's also got a wider band of superrotation, almost 40 degrees of superrotation at the equator. Jupiter's band of superrotating, depending on, is about 20 degrees or less. You probably understand that because of the difference in the size of the planets and the deepness of that the jets extend to. We'll come to that a little bit later. But you can see Jupiter and Saturn on the same plot here. In some contrast, the ice giants, Uranus and Neptune, do not. I think that is actually remains a little bit of a mystery as to why they don't. Many arguments, but insufficient observations to tell. They're also actually rotating reasonably quickly, 16 and 17 hours. They're much bigger than Earth, so in a sense their effective rotation is much larger than Earth, because in a way the effective rotation of a planet is its rotation rate multiplied by its radius. It's a non-dimensional number that comes in. But they don't. They both have retrograde motion at the equator. It's possibly due to the smaller geothermal flux, and they're not being forced by bubbling convection from the bottom. The other class of planets that seems to rotate, well, you know, Jupiter is whizzing round. Its rotation period is about 10 hours. Its radius is 10 times larger than us, and it's got a lot of convection coming up from the bottom. In some contrast, Venus has a rotation period of about 200 days. But its zonal flow is also whizzing round. We can measure that. It's about 100 meters per second at the equator. Strong zonal flow, much weaker meridional flow. And Titan, a few observations, but a probe did go in. The Huygens Cassini probe was dropped 20 years ago, I guess now. And you see that it's strongly superrotating, at least at this instant in time, and most likely more persistently, up to about 100 meters per second. Titan is a third the radius or so of Earth, and its rotation period is about 15 days. So it is also really slowly rotating. Here's Venus again. You can actually measure the zonal wind. It's rotating the other way around, if you will, compared to the other planets in the solar system. So it's, but this this is latitude, zonal wind, minus 100 meters per second, but it's still prograde relative to the direction of the flow. Here I flipped it to look a bit more normal. So it's prograde to about 50 or 60 degrees on either side of the equator. So it superrotates. Very different from Venus, from Jupiter. Final class of planets which are known to superrotate, or strongly believed to superrotate, are exoplanets, for which we have the observations are much less detailed. On the other hand, there's about 5,000 of them so far, so there's a bigger sample. But what you can measure is the flux coming from the planet and from the star and the planet which orbits it. And of course the planet goes in front of the star once a period, and it goes behind the star once a period. And here's the total flux coming from the system. And as it goes in front of the star, it reduces quite a lot. As it goes behind the star, it also reduces quite a lot, because you're getting less reflected flux from the planet, because it's now behind the star. So when it's fully behind the star, you're just getting the flux from the star. You might kind of expect that the radiation that you receive when the planet is neither in front of the star nor behind the star would be more or less the same, but it's not. It varies a little bit, and it's more just before it goes behind the star than when it comes out of the star. So here's the planet going around the star. When the planet is in this position, you're getting more radiation from the system than when it is in this position, even though the geometry looks the same. And that's generally interpreted as evidence that it is superrotating. because if it's superrotating, you see the planet is going around the same way as its orbit. Then if it weren't superrotating, you'd expect the hotspot to be in the substellar points right underneath the Sun. But if it's superrotating, the hotspot is going to be advected downstream, and so just before it goes behind the planet, the hotspot will be facing you, and you'll get more radiation. When it just comes out of the orbit behind the planet, the hotspot is facing away from you, so you'll get less radiation. And that's what you see in this plot here. One of many such plots. This kind of plot is very common. And as I mentioned, that's been interpreted as a superrotation, and here's a sort of the best inversion you can do as to where the hotspot is with such limited data. But more or less, no matter how you do the inversion, the hotspot is downstream of the substellar point. Yeah?
I'm listening to the interpreting, but wouldn't you have the same argument close to zero on the left and on the right? When you're looking at it, not coming back, not here on the left.
Oh, and here? Yeah, you'd have this. Yeah, you'd potentially have the same arguments. Well, wait a minute, let's just look at this. Well, first off, it's more symmetric there than it is here. So you're expecting it to be there. You're expecting the hotspot to be there slightly. So that's slightly more. That's still facing you more than it is here. So you would. So when it comes out of this region, the hotspot is facing you more than it is there. So you would expect it to be slightly higher here than it is here, and it is slightly higher there than it is here. So I think we're okay. I think if you stare at it for long enough, it works the way we expect it to. So, three kinds of planets superrotate, or the atmospheres of three kinds of planets. Slow rotators, namely Venus and Titan, and Mars seems to be on the edge of it. Tidally locked exoplanets, at least some of them, and the gas giants. Want to know what the mechanisms are of those, and are they related? These top two are, well, we'll treat them at least as shallow atmospheres, like Earth. Earth's atmosphere is shallow, 100 kilometers depth, if you will, 10,000 kilometers from pole to equator, so it's shallow. The gas giants certainly have a deep atmosphere. Why is superrotation surprising in the first instance? Why is it not an everyday occurrence, so to speak? It's because angular momentum of a ring of air is conserved. So if you imagine a parcel here whizzing around the planet, and we move it polewards, it will conserve its angular momentum and spin faster. So it will spin faster relative to the Earth when it's here. It's moved closer to the axis of rotation. Or similarly, if it were to move from mid-latitudes to the equator, it would, if it conserves its angular momentum, it would spin slower. So it would be going retrograde. So you don't get superrotation if there's axisymmetric motion like this. More mathematically, if you will, start out with the momentum equation, which looks something like this. U is the zonal velocity. This is the Coriolis term. Pressure term and a dissipation term. If you zonally average this equation, the pressure term goes away more or less, and if you rearrange, you get this equation, which is a conservation dm dt is just equal to the a dissipation term, and m is this expression here. It's an angular momentum of the zonally averaged velocity. Now, so angular momentum is conserved except for a dissipation term, angular momentum of the zonally averaged flow. So if you have an advected tracer and dissipation on the right-hand side, you can't have a maximum of that in the interior, and that's an old result. Goes back to the related ones go back to Prandtl and Batchelor. Here, m is just angular momentum, so if you apply this to angular momentum, you can't get any internal maximum of angular momentum in the flow interior. So that's known as Hyde's theorem. So, of course, that only applies for axis-symmetric flow. If it's not axis-symmetric flow, you've got pressure terms. So eddies can do it. So you must have eddies. And eddies create jets. And they create jets by, among other things, by making themselves into a banana shape like this. And if they make themselves into a banana shape like this, we saw some similar shaped eddies in the plasma talk the other day. They can converge momentum in the interior and accelerate the flow. Why should they do that? Why should they create themselves? This is and it turns out that the reason they do it is because if it's not fully turbulent flow, if there are waves, Rossby waves going on in it, then you can show that the momentum flux is actually proportional to the negative of the group velocity in the y direction. So here's just a little. So this is an equation which atmospheric scientists use all the time for theoretical studies, quasi-geostrophic equations. It's actually pretty similar to the Hasegawa-Mima equation, if you're more familiar with that. Take that equation, linearize it, find out the group velocity. Find out the group velocity is this expression, which is the negative of the momentum flux, uv, because u and v are related to the stream function by this expression. So that's a key result. First noticed, I think, by a man called Rory Thompson. So in mid-latitudes, for example, if you can imagine that suppose this is the Earth's atmosphere and you're stirring it for whatever reason in the middle because there's some of the instabilities going on, it creates these Rossby waves which have to, the group velocity has to be away from the disturbance region. And if the group velocity is away from the disturbance region, their momentum must converge towards the disturbance region, and you create a jet. And that's all well and good. That's understood for jets in mid-latitude atmosphere. It doesn't really work at the equator, except that insofar as you have to have eddies, because there's no obvious source for such eddies at the equator. You've got Kelvin waves and not Rossby waves, and so on. And gas giants, different again. And they're different because, well, there's no bottom to them. Here's a sketch of Jupiter's interior from a review article by Dave Stevenson recently. And here's a sort of a schematic of that, if you will. Jupiter's about 70,000 kilometers in radius. Mostly hydrogen, bit of helium. Down towards the center it becomes metallic because of the enormous pressures. But up here it's a gas, it's molecular hydrogen. And generally believe that if you go down to about 3,000 kilometers or so. Magnetic fields are not important, and you can treat it somewhat as an ideal gas. It's not ideal if you go deeper. And the Juno observations suggest that about 3,000 kilometers is the depth to which the jets go. So if it's whizzing round rapidly, the Vosvin number is small, 0.01, something like that. The notion is that the jets, or the flow, forms itself into Taylor columns like this, an idea first, I think, proposed by Buser. And they will just extend in. Well, I think Buser thought they might go further in. Now thought that they stop at about 3,000 kilometers. Okay, so why should this arrangement give you superrotation at the equator? I think it does because, well, there is an argument that it does. And the argument, simplest way you argue is that these columns will conserve their potential vorticity as they move around. But if you imagine that this is, for the sake of simplicity, if you will, a shallow water layer, then their potential vorticity is 2 omega plus the relative vorticity zeta over h, h being the height of the column, or it is on an average q minus 2 omega minus du dy over h. Now, because PV in this approximation obeys that equation, dq dt equals del squared psi, and if you suppose it's turbulence, you suppose that it will try to homogenize, and that, again, sort of origins in Prandtl-Batchelor, but also in Rines and Young ideas for ocean gyres in Earth's oceans, that they homogenize to the extent that they can. They push out the PV to the edge of the gyres and homogenize. Okay, so let's accept that, but then why does that produce superrotation? Because, okay, here's PV again. The thing, it's a bit different than Earth's atmosphere. In Earth's atmosphere, the beta effect comes from the fact that the component of Earth's rotation that you think is important is the vertical, is aligned with gravity, and that component varies with latitude. So on Earth's atmosphere, you think omega is changing with latitude, and that gives you the beta effect. But here, it's actually the length of these columns which is the important change. So if you suppose that h is changing, you can approximate this with a sort of a QG-like approximation, you end up with this expression for the potential vorticity, which is perhaps being homogenized, and this beta star is minus 2 omega over the mean h multiplied by dh dy, or the rate of change of the column with latitude. Now let's suppose that PV gets homogenized. Then, just after just a little bit of algebra, and assuming a boundary condition of du dy at the equator, so it's symmetric across the equator, you get this expression for the zonal velocity. Beta star is now negative. So that means that u diminishes as you go away from the equator. So the u is actually, if PV homogenizes this way, that u is a maximum at the equator. And I think that's we don't know that that argument is the correct one, but I think it's a compelling one and perhaps more compelling than other somewhat roundabout arguments that one has seen. Just what do numerical simulations do? We and a few others have done some. What I've just been doing in the past few months, actually, with Lorne Matilsky, who's been doing the work. Lorne's a postdoc at UCSC, and we use Rayleigh, which is a spherical code, works on the entire ball if you wanted to. We do some long simulations at fairly high resolution. This is just showing the actual vorticity, but I think I don't want to go through all the nitty-gritty details, but we force it by having a heating at the bottom and a cooling at the top. So it's a little bit like Rayleigh-Bénard convection, except it's in a spherical shell and it's rapidly rotating, and we've chosen to force it not through a diffusive flux at the bottom and a diffusive flux out of the top, because you get into all sorts of troubles that way about whether the flow is diffusively constrained or not, and we can avoid that to some degree by putting heating at the bottom and cooling at the top. And what you actually get is indeed jet formation. Here's an early part of the simulation. But no matter what we do, we always get superrotation at the equator. And the jets, you can see this is essentially the zonal velocity, superrotation at the equator, and alternating jets as you go to higher latitude. This after 1,000 rotation periods. What we're still struggling to understand with is after, this is quite a big integration. So this ran for 35,000 Jovian days. So the jets in the outer part actually seem to weaken. And the jet at the equator stays and gets stronger. We don't know really what's happening up here. But since this is a talk on superrotation, don't need to explain that. Just to note that we do get superrotation at the equator. And that's quite strong and very persistent, almost unavoidable in this kind of simulation. Others have found something similar. Nobody's quite integrated as long as we have. So, yes?
Back to your argument, and if I understood correctly, it's h, the height decreasing towards the equator.
The height actually increases. Yes, the height decreases towards the.
It gives you the superrotation, but
yeah.
with respect to mid-latitudes, you would have the same argument, wouldn't you, for the poles?
Well, you have this. Yeah, this in mid-latitudes, once you're inside this boundary, inside a tangent cylinder, as people refer to it, h actually diminishes as you go polewards. But you have a similar argument, except that you would have a similar argument, except that I think what is happening up here is that the beta, well, two things are happening up here. The rate of change of h is actually smaller when you're closer to the pole. Beta is smaller in magnitude. So you don't get this argument nearly as strongly. And secondly, there's likely actually another layer on top of this convecting layer, which is stably stratified, and it also beta will be weak, and it seems like from observations you get much more vortical motion than you get jets up here, and in fact you observe a ring of jets around the pole. So I think primarily it's because beta is small near the equator, near the pole.
So do you see PV homogenization?
We haven't actually got that far yet. This is like Lauren sent me these slides yesterday, actually, and so I hate it when people say this is hot off the press, but so I don't. Now, well, let me just show you something else, though. That's sample simulation. Regarding that, so here's, I kind of think, a more complete view of Jupiter is that you have a weather layer on top, and in that weather layer it's stratified, not convecting nearly so much. N von Weissler frequency is bigger than omega by a factor of 10 or possibly 100, so gravity takes over than rotation. This is Jupiter's absolute vorticity from a paper by Peter Reed. And you see this PV staircase oddly enough outside of the exotropics. But what Peter is plotting here is the absolute vorticity, assuming that omega is changing, not that H is changing. So that remains to be done. It's the next on the list, Peter. But oddly enough, insofar as you're getting a PV staircase here with the absolute vorticity, i.e. with relative vorticity plus beta y, that implies that there's a shallow layer here homogenizing PV. And I don't, well, it remains to be seen after analysis of these simulations as to how well PV is homogenized. So let's shift gears a little bit to terrestrial atmospheres. Oops. Just here's a plot of a numerical simulation we did with a Earth-like atmospheric general circulation model. Basically we took a model you might forecast the weather with, but stripped out a lot of the complicated physics and forced it in a rather simple way, still an Earth-like way. So this is an Earth-like rotation, and you've got jets in mid-latitudes, and westward flow at the equator, so no superrotation. And we decrease the superrotation by a factor of 5, getting closer to Mars, factor of 20, closer to Titan, factor of 100, closer to Venus. And what you can see is that the jets actually, middle altitude jets move polewards, but also it starts to superrotate at the equator, and you can see that by this plot of angular momentum. Here we're plotting the angular momentum m, that expression I showed you before, normalized by the Earth's angular momentum, -1, so you're seeing the excess angular momentum over that the Earth has. And you can see that you're really getting strong superrotation at slow rotation periods, and that's I think a fairly robust result. We get it almost no matter what you do, and I guess in a way because it's rotating faster than the Earth, it's general way, it's anti-diffusive, if you will. So what causes that? Well, we know that on Earth, in Earth's atmosphere, we have baroclinic instability in mid-latitudes that causes Wobbsey waves. And you get mid-latitude jets. On a slow rotator, the linear problem can still tell you quite a bit, but not it's a different picture. So what we do here is we take a very simple planet. It's actually just got two vertical layers, but it's pyramid of equations, and we set up a basic state which has a temperature or heating which is highest at the equator, cold at the pole. So there's a temperature gradient between the equator and the pole. There's a temperature gradient between the equator and the pole. Then just by thermal wind balance, you get a shear, and that shear is mainly in mid-latitudes here. So this is the shear associated with that basic state. So this is an exact basic state. And then we calculate the instability properties of this. That used to be a difficult thing to do, but with the advent of some modern codes, in particular Daedalus, for this, you sort of say, hey Daedalus, calculate the eigenmodes, and it does it for you. Not quite that simple, but it's fairly simple. And what do we get? We get a pattern like this. And what this has is you can see it creates what one might recognize as Kelvin lobes at the equator associated with Kelvin waves at the equator with Rossby waves off the equator. It looks a bit like the Gill pattern, for those familiar with that, which I'll come to in a minute. And that converges momentum towards the equator, and here are the eddy fluxes. So it's an instability which is then converging momentum towards the equator, which gives you the superrotation. As I say, it's a two-level eigenvalue problem on the sphere. And the key things that you need for this are an interaction between the Kelvin wave near the equator and the Rossby waves off the equator. And you don't get that in Earth's atmosphere. The ingredients that you actually need for it are here. So you need an interaction between a Kelvin wave and an off-equatorial Rossby wave. That can only occur with slow rotation for a couple of reasons. Because you need both a sort of a temporal coincidence, the frequencies have to match, and they have to be reasonably, actually, close to each other.
This is a linear coupling?
This is a, yes, I guess you would call this this is a linear calculation.
Crossing.
This is, yeah, it's modes crossing. Modes crossing. But in order for the modes to cross, the Kelvin wave has to be reasonably broad in latitude, and that will only occur at slow rotation periods. It's on Earth, for example, the Kelvin wave just expands about 1,000 kilometers, doesn't reach the Rossby waves. Slow rotation it will. You also need a jet in mid-latitudes, which slows the Rossby wave, because the Rossby waves tend to propagate. Westward, you need to Doppler shift that, so it can interact with the Kelvin wave. And that, I think, ultimately is the basic mechanism for getting superrotation in slowly rotating planets like Venus and Titan. There's quite a lot of there's lots of details actually which I may or may not get to in this talk as to when you will get that interaction and when you won't. You won't always get it because the modes don't always cross, essentially. And turns out you also need more than one layer in the vertical to get this interaction. But again, let me come to that. I think it's, nonetheless, it's still a Rossby wave, Kelvin wave interaction, and I think that was first suggested, I think, by Wang and Mitchell.
I could ask, one can imagine that they're close but no cookie. In other words, they're almost kind of close to crossing but not there. Are there players in the atmosphere that could kind of kick, you know, some mixing or something that...
I think there probably are. Not on Earth's atmosphere, because I think you're not even close on Earth's atmosphere.
Right, okay, sure.
But I think on something like Mars seems to superrotate some of the time. I mean, you do have other things going on. If you have a shear like this, you're probably going to get bioclinic instability as well. So it's going to become a bit of a mess in reality. I'll show you some non-linear simulations toward the end. Tidally locked planets are sort of the same, but different. The forcing is quite different. So on a tidally locked planet, your solar forcing is located basically at one particular location in longitude, the sub-stellar point, and you have quite intense heating at the sub-stellar point, and then, you know, because it's a sphere, it's isotropic, you know, around that point, and it's very dark on, you know, on the other side, and it's dark, very dark at the poles. So, what does that remind one of if you're an Earth scientist, this Earth? It reminds you of the problem which Adrian Gill looked at many years ago, when he was actually thinking of a different problem of how you forced Earth's tropical atmosphere with a sea surface temperature anomaly. So you've got the Earth's tropics. It's warmer. The sea surface is warmer in some places than others, and he did this problem. And this is, so again, this is a little bit similar to Gill's problem. It's essentially Gill's problem put on the sphere and done with actually two-level or multi-level primitive equations rather than the shallow water equations, which is what Gill did. So it's a little bit more realistic. But this is the actual Gill solution. And you can actually see it's fairly similar to the well, let's just go back a few. This is the instability problem just for a regular slowly rotating planet with a Kelvin mode and two Rossby modes crossing. here's actually just not an instability problem so much, but this is the linear solution to a forcing which looks like this. So that linear solution itself.
This was by the equatorial Rossby radius. So you assumed an equatorial Rossby radius here, right?
Yes, I have.
Larger than.
It's larger than on Earth's.
Yeah.
Yes, it is. It is larger than on Earth's. Considerably larger than on, and yeah. Oh, can't remember what it is. But this is also basically a slowly rotating, tidally locked planet. I think its rotation period is maybe of the order of 10 days, 10 Earth days. And again, then if you calculate the eddy fluxes due to this pattern, they converge towards the equator and give you superrotation. There's a slight, again, there's some technical issues in a single layer. You actually don't get that. Because if you're symmetric across the equator, the eddy fluxes identically vanish at the equator in a single level model, because you can write them in this form: V primed, zeta primed. If everything is symmetric across the equator, that term vanishes. But as soon as you have multiple levels, that problem goes away. So you're getting pretty similar results, in a sense, or pretty similar mechanisms between slowly rotating planets and tidally locked planets. Basically, you need eddies to drive superrotation. On giant planets, you get columnar flows give rise to the superrotation. On slow rotators, we're arguing there's a planetary scale Rossby-Kelvin wave instability, a mode coupling, if you like, that gives rise to equatorial acceleration. On tidally locked planets, you don't need this instability in the same way because you have standing Kelvin and Rossby waves, but you do still need the temporal proximity of Kelvin and Rossby waves for that interaction. And here, as Peter said, I've increased the Rossby radius of deformation considerably to get that interaction. It passes it. The details matter. I could go into the details, or I could just, since I've been going for 50 minutes, I could just stop here if you like.
You don't want to miss out on Daedalus, do you, David?
You want some Daedalus details?
I'll go through the details very quickly, just a hint of what they are, and then, you know, professionals or whoever can, as I say, single layer model can't do it. All these results were with Daedalus. The deep stuff was done with this big code called Rayleigh. One way round that, which was done by Adam Sherman, was to take a single layer model and add a slightly, perhaps ad hoc parameterization of heating to it, which actually put heat source into the layer depending upon what its velocity was, and that gave him superrotation. We didn't really like that, so we added a vertical structure to a model. Well, all of this stuff we did it with a two-level model because we could actually still get analytic gill-like solutions for it, but it avoided this problem of the single layer. Then oh, things varied. We compared some of the nonlinear solutions with the actual gill pattern. Depending on parameters, the linear solution did better, did fairly well here, did worse there. It actually did pretty well if we didn't do exactly the gill problem, but we added a velocity field to it at the equator. Then we got very good agreement between a simulation spin-up and a gill pattern. The pattern of heating actually matters. As I mentioned, if you only get the superrotation in slowly rotating planets because the Kelvin wave has to expand sufficiently far in mid-latitudes to interact with the Rossby waves. And that also ends up being a function of the pattern of the heating. And if the pattern of the heating is more like this, it seems to push out the Rossby waves too far polewards to interact, and you don't get any superrotation. But here, and I think this actually resembles more what an exoplanet will be, you do get superrotation. Finally, just to sort of connect tidally locked planets and axisymmetrically forced planets like Venus or something like that, if you can actually decompose the heating that you get in a tidally locked planet to be an axisymmetric heating, as you would get on a regular planet, plus a wave number 1 forcing. And if you add this and this, you get what the tidally locked forcing is. That allows you to actually, in a way, pass in parameter space between a tidally locked planet and a slowly rotating planet just by reducing the effects of the wave number 1 heating. So we can actually sort of pass from one to the other in parameter space. And it turns out that if we do that, this is a wave number frequency plot. Omega is on this axis. When you've got axisymmetric forcing, and this is a nonlinear solution, so all these little blue and red contours imply that there's power at this particular frequency, another wave number which I've missed out the label of here. Purely axisymmetric, lots of modes interacting. If we make it just slightly almost axisymmetric by adding a very small amplitude to the wave number 1 forcing, that almost immediately dominates. So the tidally locked planets are actually, in a way, more efficient at producing superrotation than slow rotators. But I will stop here, and I'll just let you read the conclusions. Thanks.
Thank you, Jeff. Thank you very much. Question? Please.
Thanks, Jeff, for a nice talk. This might be related to what you showed at the end, but do you know how this interacts with mid-latitude baroclinic instability? Could you have a mid-latitude jet and superrotation?
Yeah, we did have that. Well, it would have been there. It would have been there.
You only had one jet in the velocity profiles you showed in the next slide. It was there in the top there.
Well, one jet in.
Well, one per hemisphere.
One per hemisphere, yeah. So that's the so that's your, if you will, your mid-latitude jet, and that's your superrotating jet.
You never have both.
Oh, we never have both. Well, it appears we never have both. Yeah. Yes, it flips, doesn't it? Yeah, I think that would be hard to get, actually, because it's this interaction that you want to get. So that's going to mess up your mid-latitude jets, I think, quite a bit.
Isn't your middle curve Earth?
Middle curve, yeah, the middle curve.
It's got a positive view.
It's got positive, but it's not a local maximum, though, is it?
Well, but okay. Well, then are you saying superrotation is only used as a term when you have a local maximum?
No, I wasn't saying that. But John was asking whether I can get. Well, my interpretation of his question was whether you can get a distinct local maximum at the equator and in mid-latitude, and we've never seen that. But indeed, we do get superrotation in this case. So we can get superrotation with a mid-latitude jet, but not a local. We don't get a local maximum with a local.
So you're leading us on with this very suggestive comment of, are all exoplanets superrotating? And why do you think that?
I don't think that.
I mean, it seems to me hot Jupiters are excellent candidates, but they're obviously not the only.
No, I think, well, the reason I say that is that we had the summer school last summer at Woods Hole, and there were some exoplanet observers, and they sort of somehow got it in their head, it seemed to me, that exoplanets superrotated. And most of the ones which have been discovered do, if I can go back, we, have, well, you can see two examples here, do have this kind of phase curve implying superrotation. But, I mean, in the nonlinear simulations that we've done, quite a few of them do not superrotate. And I actually think, but I'm not sure at all, that tidally locked sort of terrestrial planets might superrotate more than tidally locked hot Jupiters. The reason I say that is that we found, I can show one of the figures, maybe not, that bottom friction was important. Don't know whether I have a slide or not. Oh, yeah. So just as an example slide, here are some various simulations with no bottom friction. E is Ekman number, if you like. So this simulation has no bottom friction, does not superrotate. Bottom friction always helped in our superrotation because the vertical transport of momentum was important. And if you had bottom friction and not friction above, the lower layer got out of phase with the upper layer, and you could actually get a transfer of momentum vertically, which helped. And I think there was a paper in somewhere like Nature or Nature Astronomy of somebody who'd found a tidally locked planet which wasn't superrotating. And the fact that this discovery got them into a paper in Nature made me think that, oh, well, they think that's unusual.
Just if I could, a quick follow-up, what would you suggest to the observers as a way to illuminate this issue?
Well, I suppose I would like some kind of classification of the planets which did superrotate and which didn't, and for them to sort of try and put them into categories like super Earths or sub-Neptunes versus hot Jupiters which superrotate, and I would like a little bit more detail maybe about the pole to equator temperature gradients. I think that would help too. So, but when I was chatting with Heather Knudsen, who's an observer, and she made the analogy, well, you know, what we're trying to do is observe, we're in Los Angeles and we're trying to observe two fireflies in New York circling each other. And so it's a tricky one, I think. So they do best they can. Yeah.
You're mentioning in the conclusions that the mechanisms for the gas giants are different from.
Well, yeah, go on.
They're different from the other two, but would it be a stretch to think that, for instance, in the case of Jupiter, you have your great red spot sitting there? Would it be an analog of your Gale cell, and it would create, and it would contribute to superrotation as well?
I think debates about what the great red spots are. The great red spot is too far off the equator for it to be a Gill-like solution. So I don't think it can be. I mean, most arguments of the great red spot argue that it's somehow close to being an exact vortex which perpetuates itself and it's fed by other vortices coming in. So I haven't seen any arguments like that. So I wouldn't want to be the one to propose that. I think it would have to be somebody braver.
Is there any other explanation, like a moon or something? Would that work?
For the great red spot?
No, for the exoplanet. Like if there's a moon rotating around the planet and it's rotating at twice the frequency or something.
Oh, I see. Or might the moon give rise to superrotation?
Yeah.
I suppose it might, but I think I'd invert Occam's razor to that. We don't know that these exoplanets have moons. I suspect most of them don't. So I think I'd say that was a speculative argument. Chris had a...
Yeah, I mean, you make a distinction between the shallow atmospheres and
Yeah.
deep atmospheres. I think that's important, because as soon as you start talking about deep atmospheres, of course, then the question of stars actually comes into play, because all these things have been discussed in the context of stars as well as planets.
Yeah.
The idea is usually that it's all a question of the Rossby number. If the Rossby number is small, then the thing superrotates.
Yeah.
Just like in your sort of Jupiter picture, which is basically a low Rossby number picture. And but then when you go to a higher Rossby number, then you can get things going westward at the equator.
Yeah.
So
Yeah, you can. Right.
Twist to this story.
Yeah. Yeah, there's a million stories.
I mean, this is also relevant to the question you were asking about whether you get superrotation on all exoplanets, because the exoplanets that will have a variation in Rossby numbers.
Yeah, they have a variation in Rossby numbers. That's right. Yeah. I mean, the ones which I showed observations for have relatively high Rossby numbers, slow rotation rates. As for Jupiter, yeah, well, we know that Jupiter has a low Rossby number. That's one thing we do know. But it's interesting, though, that this, for example, something that we haven't fully understood is that early on, and I think this actually is the same as what other people have reported, that we do get multiple jets. As we go to, this is quite a long, very long integration. These extratropical jets actually seem to go away. And this simulation, my collaborators in this, they're all stellar astrophysicists. And they said, oh, it's starting to look like the sun, which just has really one big jet. So the question remains, actually, which I kind of wonder about, is it if there is a weather layer on top of this, you get different dynamics in the weather layer, and you get more Earth-like dynamics in the weather layer. And then maybe that's the key to getting multiple jets.
There are studies of people that study exoplanets for whom the magnetic field is hugely responsible. It's the big thing.
Yeah.
That's just going to change all your waves, everything. Is that right?
Well, for the ones that it does, yes. Whether that's true of all exoplanets, and
there are so many exoplanets, it's bound to be true in some and not to be true in others.
Yeah, and the other thing about exoplanets, you know, even hot Jupiters, they're being blasted by radiation from their star. They're getting thousands of watts per square meter from their star. They're probably getting a few or maybe tens of watts per square meter from their interior. So I think that by far the dominant thermal forcing is actually coming from above and not from underneath, and so that motion, I suspect, will be maybe relatively shallow. So in that sense, modelling them with a shallow atmosphere might not be so bad, a neutral shallow atmosphere. But yeah, your point is taken. One thing at a time. Yeah.
Yes.
Can it happen that those superrotating flows become unstable at some point?
I mean, you know, in a way they are unstable, but they don't seem to be unstable to any sort of large-scale meandering instability. You know, in the sense of a barotropic instability, which would make them meander. So they don't seem to be like that. Although I think it's a good question, because if you actually look at the just do the simplest thing, certainly away from the equatorial region, and look at the Rayleigh-Quo criterion, which is the simplest one for barotropic instability. Some of the jets do seem as if they would violate that criterion for instability and would be unstable. So I don't think that's been properly explained, because the observational evidence is that these jets have hardly moved. I mean, you know, we know the Great Red Spot was observed by Galileo, and these are these various different lines that you can see. Well, one's from Voyager, 1979. One is from the Hubble Space Telescope, about 35 years later. And the jets are all almost in exactly the same place. So in that sense, they are not unstable, sort of, by that criterion.
Right, okay, I think we're done. So two things. First, let's thank Geoff again for a very interesting talk.